就是现在有几个学生是大四的，我一直有2个大四的学生在我的班里的 roster 上面，但我一直都没有看到他们，所以我不知道他们是挂什么？你说什么？
那我在跟他学的。
就是现在我们有1、2、3、4、5、6、7、8，还有别的学生吗？那你后面是不是有一个人？啊？哦，你外套是吧？就是很像我们刚过那个线是吧？就是这个班应该还可以开得成啊。挺高兴。好，你说什么？
我说扣掉那2个大四的也还剩8。
哦，行，好，很像我还多了一个大2的，但是那个人好像没来上，我不知道那个人是谁，我也不拿就是我也不看你们有没有，I don't take roles, right? I don't know who actually comes to this class, but so long as I have 8, we're good to go. So, last time, okay, you guys asked me to give you guys some examples, right, for your class. This book is very good for that, okay? So, this book is very similar to your textbook for thermodynamics, okay, the NES class. It's your authors for your thermodynamics class. The text that you use for that class is by the NES, right? 你还没有学。Okay, that's fine. You will, okay? So, there's a lot of examples in this book, okay? So, we'll go through some of these examples. So, last class we started talking about the thermodynamics. Okay? And we derived the Nernst equation. So, we'll start by talking about the Faraday's law, and then go over some of the applications. Okay? So, Faraday's law is it's a law that we can use to relate the amount of current, okay, that passes through the thermal conductor to the amount of mass, okay, produced or consumed, okay. Okay, for example, okay, so we have a zinc, okay, and this is a solid, okay, and then if you guys want to follow this is from chapter 2, okay, I think chapter 2, section 3 of your textbook, okay. If you want to read this book, pass it around.
是第6页，你现在讲这边。
对，你们要吗？要看这本吗？谁要看？ Okay. So the zinc solid is going to dissociate into zinc 2 plus 2 electrons. Okay, this is aqueous. Okay. So for every moles of zinc, there is 2 moles of electron. Okay. So Faraday's law, okay, is Q is equal to I dt. Okay. And I, okay, the should be the total number charged, okay? So, so to relate, okay, the amount of current that's either consumed or produced to the mass that's produced or consumed, okay? Current data laws have this form, okay? So MI, this is the mass of PCI. Okay. And this is equal to the molecular weight of this PCI. This is in gram per mole. Times the charge, okay, which is in coulombs. Divided by n, okay, which is in charge, okay. So this, okay, is n, and it's 2, okay. And then divided by the stoichiometric coefficient, okay. So, and this would give you equivalent of charge, okay, per mole, okay. And then times the Faraday's constant, okay, which is C, for equivalent. Okay. So this is Faraday's law. Okay. So for instance, okay, the applications of Faraday's law. So how much, examples, okay, so for a current of 1 amp, okay, I'm sorry, 12 amps, okay, 12 amps, that passes for 2 hours. So, how many zinc react? Okay. So using the Faraday's law, okay, you can simply be Mi is equal to, so the zinc has 65.38 grams per mole, okay. Then you have 12 amps, which is the same as coulomb per second, okay? Coulomb per second. Okay. So you have 2 hours. 2 hours. 2 hours. Okay. 1 hour is 3,600 seconds. Okay. And then divide that by n is 2, okay, over 1, which is the stoichiometric coefficient, okay, of zinc, okay. So 2 electrons per mole zinc, okay. So, times 9, 6,485, this is the Faraday's constant, okay. You get 29.3 gram of zinc. Okay. This is what. Oh, this is the stoichiometric coefficient. 1.
哦，所以是那个吗？
啊？
所以是
对，这是前面的数字。1 mole of zinc becomes 1 mole of zinc aqueous, and then you get 2 electrons. So this is a process. This is a process to derive the number of for electrolytic synthesis So just take 12 amps, you get 29.3 grams of zinc. Okay. So, um, this is an energy intensive process. Okay. Recently, BASF, okay, they moved all their electrolytic synthesis of zinc, okay, from Germany to a portion of it to US and a portion of it, I think, to China because they ran out of cheap energy. This is the process. Okay. Okay. So one more thing. Okay. So if for this process, okay, if the efficiency is 100%, okay, then you would require 12 amps, okay. But let's say, okay, you know the Faraday efficiency, okay. So this is the Faraday efficiency. Is like 96%, okay, which is fairly common, okay. How much energy would you actually need to output this much zinc? Okay. So you just divide 12 by 0.96, right? You calculate whatever that is to find the energy actual. Right? Right. Okay. And the difference between the energy actual and the energy theoretical is the extra amount that you.
对不对？这样会变大。
对啊，这就要变大。
为什么？
因为你真正用的东西真正用的电会比你 theoretical 的电还要高。
哦。
对吧？
哦。
Right?
哦，可以。
And whatever that difference is due to the side reactions. Okay. We're going to talk about those side reactions later. Okay. But for the most part, side reactions are if it's an aqueous process. Okay. If it happens in an electrolyte, like the hydrogen evolution is a common side reaction. Okay. And with the generation of hydrogen, okay, you have the process of the associated problem of like corrosion, okay, because hydrogen is acidic. Okay. Just going over some of the basic concepts. Okay. And so, okay. So if you have, if you're doing this process in a cell, okay, and your electrode, okay, area, okay, is 80 centimeters, okay. Keep in mind that this is a heterogeneous process, okay. We talked about that last time. And what it means is it's area dependent, okay. It happens only on the surface of the electrode. Okay. So just to do a quick calculation, so if the area is 80 centimeters, okay, which is slightly less than 10 centimeter by 10 centimeter, okay. It's about so what is the current density? Okay, So what is the current density? It's just simply 12 divided by 0.008. Okay? This is in meters squared. Okay? Which is 1,500 amps per centimeter. Okay? So this is a quick way to calculate the current density. Okay? 什么？0.008。Okay, so potential and Ohm's law. Ohm's law. Okay. So sometimes I will write the potential as this. Okay, and sometimes I will write it as that. Okay, but they're the same. Okay. So electrostatic potential. Okay. So electrostatic potential. Okay. Is equal to work required to move a unit charge from X to Y. Okay? And usually, since this is a heterogeneous process, it's electrosurface. Okay? It could be from another electrosurface to the electrosurface, or it could be from electrolyte to electrosurface. Anyway, okay? So the electrostatic potential. Okay? This has units of volts. Okay? And which is equivalent to joules per coulomb. Okay? So here is volts. This is unit of energy. Okay? So this is joules per coulomb. Okay? Whereas here, amp is this is amp is a unit of flow of charge. Okay? Note the difference. Okay? This is flow of charge. This is energy per charge. Okay? If you keep the units in mind, then you won't get confused when we talk about how potentials is related to current. Okay? So this is a measure. So this electrostatic potential is a measure, okay, of energy, of electron in the metal. Okay. So in essence, okay, if you measure the electrostatic potential between two electrodes, okay, that's the difference in energy, okay, between the two electrodes, okay, and cell, okay, and this is mostly a function of the thermodynamics, okay. So this is a function of the thermodynamic. Okay. And electrolyte composition. Okay. Okay. And another, so this is potential, okay? This is potential, okay? And Ohm's law. Okay. So Ohm's law, so we talked about potential and we talked about current, okay? Okay. So these are the two. So we have potential, we have mass, okay, and then we have current, okay. So we have Faraday's law that can give us the relationship between mass consumed or produced for a given current, okay. So Ohm's law, okay, it relates, okay. This is a law that relates, okay, current, okay, I, to potential, okay. So I of x, okay, is equal to minus k d dx. Okay. So this is the conductivity, which has units of centimeters per centimeter. Okay, and this is the potential, okay, and this is the current. So I'm going to start with it. So I'll start with an example. Okay. So this is an example. Okay. Of a electrochemical system. Okay. The chloro alkali complex. Okay. So we have the cell, okay? Then we have the separator, okay? And here we have 2H2O plus 2E goes to H2 plus 2OH minus. Okay? And this is the cathode. Okay? Cathode. Then we have 2 chlorine minus goes to Cl2 plus 2. Okay? This is okay? So so we have a DC that drives like this reaction, okay? So the electron here we have a concentrated sodium solution. Okay. So Na plus Cl minus. So so as this process continues, okay, this is a gas. This is a gas. Okay. So we have water. Okay. Water is going to undergo electrolysis and gives off like two hydrogen gas. Okay. So H2 is going to get synthesized here, and chlorine is going to get synthesized here. They're both gas phase. Okay. And the overall reaction is 2H2O plus 2Cl minus goes into Cl2 plus H2 plus 2OH minus. We just add these together. Okay? And so this process goes like this, okay? Constant flux of concentrated sodium chloride solution goes into this reactor, okay? And then so over here at the anode, okay? Chlorine, okay, is going to come over here, okay? And then give up its electrons. Okay? We have a sodium chloride salt, right? So like this, the chloride, okay? The solvated chloride in the solution is going to come over here, okay? Onto the surface of the electrode, and then they're gonna come together and give off two electrons, and then turn gaseous, okay? Become gas, okay? And then this electron is there's two electrons gonna come over here, okay? And then it's gonna combine with this water, and then undergo electrolysis and form hydrogen and this hydroxide. So that's why it's called chlor-alkali process. It's forming concentrated hydroxide in the solution, concentrated H2 gas in the solution, in the airspace over here. Okay, these are separated. Okay, and then concentrated Cl minus over here. Okay, so flux of sodium chloride solution is going to come over here. Okay, sodium to maintain the charge balance. Sodium ion is going to serve as the charge carrier. Okay, so this membrane is only permeable to sodium plus. Okay. And OH minus is gonna, water is gonna come to the surface, okay, and then give off two electrons to form H2. And then OH minus is gonna come off. Okay. So this process is electrolytic process. Okay, this is the electrolytic process. What it means is that it requires power. Okay? So, so without power, okay, this reaction is going to go the other way. Okay? Okay? So, and the rate of this reaction can be controlled by the power you supply, okay, by the DC power supply. Okay? So the rate of chemical reaction is proportionate to the current. Okay, that you supply. And you can dial that current to whatever rate you want. Okay. So this is the difference between normal chemical reactions versus electrochemical reactions. Okay. Normal chemical reactions, you just put everything in a pot, and depending on the pressure and temperature, you equilibrate to a certain rate. Okay. Whereas in electrochemical process, you can control the rate of reaction by the current that you apply. Okay. Okay. So this electrolytic process, okay, is again controlled through this DC power supply. Okay. You have two modes of operation. Okay. You have the constant I, the constant current mode, okay, the galvanostatic mode. Or you have the constant V, constant voltage. This is the this is the potential static mode. Static mode. Okay? So how is the amps, okay? The current varies with the voltage, okay? So what is the relationship between this current and voltage, okay? So I is a function of voltage, okay? And in this expression, Ohm's law, okay? This is a linear function, okay? I is a linear function of the potential, and that constant is the conductivity, okay? But typically, in an electrolytic process, okay, this is not a constant linear process, okay? This is more complex. And this is a function, okay, of thermodynamic, okay, kinetic, and transport. Okay? So we'll talk about this. Okay? So the basic features of how the voltage, okay, this is the dependent variable, right? So this is the voltage. Okay? Okay, this is the potential, right? So how potential varies is a function of current, okay? So I'm going to write current as current density, okay, I. Okay? So I is amps per centimeter squared. Okay? This reflects that this is a heterogeneous reaction that happens on surface. Okay?
这两个符号什么差？
什么东西？
就是那个 V 跟那个，它们不是都电压吗？
不对，这个是 potential，它不是一个单位，这个是个单位。
哦。
这是代表 potential。
那是电位的。
这个是 volts。
哦。
这个是等于coulomb per what is volts I over C. No, joule per coulombs. Okay, this is joule per coulombs. this is just potential. Okay? And this is a unit. Okay, when I write units, I'll put them in a bracket. Okay? And this is current density. Okay? So because this is a heterogeneous reaction, we divide that over the area. Okay? Okay, so for this chloralkali process, okay, so as fresh zinc, fresh sodium chloride, concentrated sodium chloride solution is constant, okay? This process occurs, okay? And so you will have a certain potential to current density relationship, okay? So this is what it looks like. So let's say this is 2, okay? And it looks like this, okay? Then this is 0, okay? So this is this is 4, okay? So this looks like this, okay? So so this is what it looks like for the chloralkali process. Okay. So a couple things to notice that so as I is equal to 0, okay, right? When the current is 0, what process? What does that mean? Current is equal to 0.
没有电流。
是这个意思吗？断的意思，对吧？就是 when current is equal to 0, okay? The voltage is not equal to 0. Okay? So this voltage right here, okay, is called the equilibrium, which is equal to 2. Okay, this is the open cell voltage or equilibrium voltage, whatever you want to call it, the same. Okay. So this is the open circuit potential or equilibrium potential. Right? Yeah. So
为什么它的电压是4？
啊。
为什么？
它就是这样，就是这两个金属决定的，还有它里面的这个，OK，所以这个是一个 function thermodynamic and electrolyte。OK，这跟这两个金属有关，还有它的 electrolyte。好吧。
所以它是随着什么减少？它是随着它的电流密度减少，它是随着。
这是你说这个是吧？这是通过它的电流来调的，就是你的它的 I 是通过它的 DC supply 来调的，对吧？在这个地方，对吧？我画个线说就是在这个地方，当这个东西是断的时候，它的 voltage 是 2，差不多。就是你拿一个 voltmeter， 对吧？就是这 voltmeter 是这样子，对吧？有两个这个东西，两个 把量调到零的时候，
我把
什么时候是吧？是负多少？
就是voltage 2以上，对吧？是你需要花多少电，让它走到这里。So this is the electrolytic process. This is the electrolytic regime. Down here is the galvanostatic regime. Okay? So, 你如果要让它到4的话，你要花很多的电，大量的电把它调到这边来，把它调到这边来。就是so the open circuit potential is 2, right? Right? So what that means, you have to provide a current that's greater than, provide a voltage that's greater than 2 in order to move the process this way. You want to do the example, okay? So using this example, okay? So what is the equilibrium potential? Okay. So if you look in the back of your book, okay, there's appendix A. Okay. You can find the equilibrium potential. Okay. So positive is CL2 plus 2E minus goes to 2CL minus. So this is 1.36 volts. Okay. And then this negative is 2H2O plus 2E minus goes to H2 plus 2OH minus. Minus 0.828 volts. Okay? Because this is positive and this is negative, right? This is the cathode. And this is the anode. Spontaneous. Okay? So if you write a full cell reaction, okay, this is Cl2 plus H2. Okay. So it's Cl2 gas plus H2 gas. CO2 is gas plus H2. This is gas, okay? Plus 2OH minus goes to 2H2O plus 2Cl minus. So the U, the cell, okay, this is the standard potential, okay, is at 25 degrees C is equal to U Cl minus So this is the standard potential, okay? I'm sorry, this is the equilibrium potential. This is the standard, they're not necessarily the same, okay? So to get the, this is the standard, okay? So to get the equilibrium potential, we have to use the thermodynamic equation that we derived last time, okay? Minus RT, and ionic species, Ci over Ci naught, Si, and Y, gas species. Pi over Pi okay. So this is that. Okay. So this is the equilibrium potential, which is equal to this. We haven't calculated that yet. Okay. So so 2.188, okay, minus R, which is 8.314 times temperature 25 plus 273, okay, over N is 2, okay, two electrons, okay, 2 times 9645, okay, and ln. Okay. This is in this example. Okay. In this example, they gave so for a 5 molar solution. Okay. So concentration is 5. Okay. And then the charge, I mean the stoichiometric coefficient is 2 here. We don't count the water because that's 0. That's equal to 1. Okay. And then again, the stoichiometric coefficient is 2 over here. Okay. So concentration is 5. Okay. So we raise that to 2. Okay. And then we have 1 squared. And then we have the gas. Okay, the gas. The gas here and gas here, okay, which is 1, okay? 1 squared, okay? And then 2 squared, okay? So you end up with a number which is 2.1. Eight minus 0.024, which is equal to 2.16. 2.1, okay? 2.1. 2.1. 2.1. Okay, something 2.1 volts. Okay, so this is what 2.1 volts. That's how you get this. Okay. So so if you're in if you want want to move the this process so that it's in the electrolytic mode, okay? You have to provide higher than 2.1 volts to push the process to reverse the process because this reaction right here, okay? It's the spontaneous reaction is it's opposite of this side, okay? So it doesn't want to move in that direction. Okay? You have to provide enough power, okay, to reverse the direction to produce the chlorines and the hydroxides. Okay? So the U that you apply, okay, gotta be greater than the U equilibrium, okay, which is greater than 2.164, okay. It has to be greater than 2.164, okay. 2.164. Okay. Any questions or? So, another example, okay? So for a lead acid battery, okay? With, again, 5 molar sulfuric acid as the electrolyte. Okay. So the reaction is this, okay? So the negative reaction is Pb. The negative reaction is Pb solvent plus SO4 2 minus goes Pb SO4 solid plus 2 electrons. Okay? And this has the standard potential of minus 0.356 volts. Okay? Negative 0.356. Then we have the positive. We have Pb, 2 solid, plus SO4, 2 minus, goes to plus 4H plus 2 this is positive, this is the cathode, okay? And this is the negative, this is the anode, okay? So, the standard potential would be therefore equal to, 1.685 minus negative 0.356, which is equal to 2.041 volts. Okay. So, the full cell reaction, okay, if you, since this is a positive, okay, would be this minus that, okay, and then if, since this electron is on the left-hand side, then that means, this electron has on the right-hand side. So, just minus these two reactions, or add these two, minus these two reactions together, you get PbO2 solid. Minus Pb. That's 2, that's 4. Minus, that's 4, that's plus. Goes to 2P. And so, 1 salt plus 2H2O. Okay. So you have 5 molar solution. Okay. You have a 5 molar solution. And so, if you have 5 molar sulfuric acid, then that means this is 5. Okay. And this is 5. And because this is solid, okay, and this is water, okay, so this is equal to 1, okay, this is solid, all this is equal to 1, okay, within the, within this, expression, okay, you only count the aqueous species, okay, these ionic species, okay, so you have, U is equal to, cell minus RT and F down at hot. CI over C naught. That's fine. Okay. So you have, so you have 2.041, this is your standard, okay? 2.041 minus R, 8.3. So this is 8.3, okay, times temperature, 25 degrees Celsius, again, N is 2, okay? 2, okay? Times the pyrrolase constant, 9645. Okay? And then you have 2 ionic species, okay, sulfate and hydrogen, okay? So, water, okay, here, this is the product, right? So product is on the top-hand side, 1. Okay? This is Ln. Okay, Ln. Water is 1, solid is 1, okay? Over reactant, okay? This is 1, so you don't count those. And then you have these 2 species, okay? 5 raised to 2, okay? And then 5, this is concentration raised to 4. Okay? Yeah? So you calculate that, you get around 2.16 volts. Okay, so this is the equilibrium potential. Okay? So the equilibrium potential is when there's open circuit. Okay, so contrary to the chloride-alkali process, okay? The lead acid is a galvanic cell, and this is a battery, okay? So when the circuit is when the circuit is closed, okay, this will spontaneously move to produce current. Okay, it will consume the lead and produce current. Whereas the chloride-alkali process, because this is the electrolytic cell. Okay? The spontaneous reaction is to this is the electrolytic process. Okay, so if you want the cell to move to produce hydrogen and chlorine gas, okay, you'll have to input energy. Okay, higher than this 2.16 volts. Okay, so so this is the illustration of some simple examples of the electrochemical systems. Okay, we have a galvanic cell, which is which we have the examples of the lead acid battery, and then we have an electrolytic cell, which we have the examples of the chloride-alkali process. Okay. The difference between the electrolytic process cell and the galvanic cell is that the galvanic cell it will spontaneously generate power, current, okay? Because it will spontaneously convert the chemical energy into current. Okay? Whereas the chloride-alkali process, you have to input energy to produce the chemicals that you want. Okay? Because the thermodynamic of this process favors the formation of the chloride ions. Okay, so this link is broken. Okay. The hydrogen and the chlorine gas will spontaneously form water and chloride. Make sense? The spontaneous process is this way. Okay? If you want to go the other way, okay? If you want, so where's the full cell reaction? This is the full cell reaction, okay? Well, yeah, this is the spontaneous process. The direction indicates the spontaneous direction of this reaction. Okay? If you have chlorine gas and hydrogen gas, okay, together, you'll spontaneously form water and chloride ions. If you want to force it to produce hydrogen gas and chlorine gas, then you have to input that extra energy. Make sense? And the energy is calculated here. You have to input that much voltage. You have to input voltage higher than 2.16 volts. Okay?
and the higher the voltage, the more stuff you produce. The higher the current, the more stuff you produce. Okay. Well, we'll stop right here. Okay.
那个氢离子多少？那个氢离子那边为什么是？